in this lecture we are going to start the concept of factor analysis. Now the original development of this factor analysis, which is one of the important applied multivariate statistical technique, is due to the psychologists Spearman and Thurston. Now before we actually go into the mathematics of factor analysis, the factor analysis is an important technique. As I said, the basic purpose of factor analysis is that we try to explain the covariance structure of a multidimensional vector through a number of underlying factors. These underlying factors are what we call unobservable random factors. So let us try to get into this concept of factor analysis. So the basic purpose is what I just now said, is that to explain the covariance structure or the variance covariance structure of a random vector in terms of a few underlying unobservable factors . Now these unobservable factors are random variables. Now there are points why it is written that in terms of a few underlying. Suppose we have got x, this is the original observed random vector, that we have. Now this x is such that expectation vector of x is equal to, say, mu, and the covariance matrix of this x random vector is given by sigma. We assume as before that sigma is positive definite. Now the factor analysis is concerned about this variance covariance structure sigma, and it tries to explain this covariance structure in terms of a few underlying but unobservable random variables. Now if we look back at principal component analysis, in principal component analysis also we were concerned about the variance covariance matrix there. Now in principal component analysis, what the objective was, that we had tried to do the following, that it was data dimension reduction without loss of information. So we were concerned about the sigma, the variance covariance matrix, and tried to explain the total variability in the data, which is measured through the trace of the sigma matrix, and tried to capture that total variation in x, the trace of sigma matrix, through a number of linear combinations of the x random variable components. Now there actually what we did was, we had from x we had made an orthogonal transformation to another space where we were looking at the space of principal components, and there through appropriate number of principal components we had tried to capture the total variability in x through a fewer number of linear combinations of x which were orthogonal among themselves. Now here also we are concerned about the variance covariance structure, the sigma matrix, and we will try to explain this covariance structure sigma in terms of a few underlying factors. We will call them as common factors. Now there actually those common factors are something which are unobservable random quantities. Let us now look at what we have as a factor model, factor analysis model. The factor analysis model is something like this, that we write x minus mu. So x is this observed random vector, mu is the mean vector corresponding to that. This is written as an L f plus epsilon. I am going to say what these are. Now suppose this p is the dimension of this observed random vector. So this side we have a p cross 1 vector. Now this L is a matrix of constants which is of the order of p by m. This f is a vector which is of the order m by 1, and this epsilon is a random vector which is going to be p by 1. Now what are these quantities L, F and epsilon? These are the terms which actually define the factor analysis, the factor model. So here what we have is this F, which is the vector of our unobservable random vector, unobservable random variables called the M. This is an m by 1 vector, so m common factors we will have later on define some, actually we will put some assumptions on this F vector in order to quantify what sort of random variable that is. Now the second thing is epsilon. Epsilon is a p by 1. Now these common factors, when we said that F is a vector of unobservable random variables called m common factors, these m common factors are common to each of the original x p dimensional random vector. Now epsilon, this is p dimensional vector, these are called specific factors. These are called specific factors specific to the ith variable. And the third quantity, as in here in this factor model, so this F is what we have as a vector of common factors, this epsilon is the vector of specific factors, the thing that is left is L. So this L is given by, this is a p by m matrix of constants. So this is L11, L12, L1m, and this is an LP1 to up to LPm. So this L is the matrix of factor loadings Now these factor loadings has got this interpretation that this Lij is the loading of the ith variable, ith original variable, variable xi on the jth common factor, jth common factor, which is fj. Now this has got an important role to play. It indicates this it of course is Lij, which we have Pm of them. It indicates the importance of xi on the jth common factor fj, and thus is important for interpretation of these common factors, right. Now this is what thus is the factor model, the factor analysis model. So we write the x observed random vector, what we have as observations. This x minus mu is written as Lf plus epsilon, wherein this L is a matrix of constants, which we are calling as the factor loadings matrix, and we have F, the vector of unobservable random variables called the common factors, and epsilon are the vectors. So we have here, it's better to write it, this F m by 1 is this vector f1 f2 fm transpose, and this epsilon is the vector, the specific factor vector, which is having these p components, which are epsilon 1, epsilon 2 up to epsilon p, right. Now if we look at this factor analysis model, this does remind us of a model in statistics which resembles this. If we look at a linear regression model, a multiple linear regression model. A multiple linear regression model looks like the following, that we write y equal to x beta plus epsilon. Now, in this setup, y is the set of response variables, or rather these are the observations in the response variable. Say this is n by 1 n observations, and beta is the vector of parameters which are involved in a multiple linear regression model. So, this say is a p by 1 dimensional vector of constants. This x is what is called the design matrix in multiple linear regression. This is of the order of n by p matrix of deterministic constants, and this epsilon is the vector of noise random variables. So, this is how the multiple linear regression model looks like. Now, if we look back at the factor analysis model, there is a similarity between the two models. Here also, if we define this to be equal to some vector y, then y is equal to LF plus epsilon. We have in the multiple linear regression model y equal to x beta plus epsilon. X is a matrix of constants. Here in the factor analysis model, L is a matrix of constants. So, what is the difference between this factor analysis model and the multiple linear regression model? The difference is that in the multiple linear regression model, we have x to come up with the values actually of independent random variables which are observable, and these are this is the vector of constants which are to be determined through the multiple linear regression model. And if we look at this factor analysis model, although it looks like the multiple linear regression model, there is a huge difference between the two models as such. Here we are having f to be the vector of this random variables which are unobservable. So, while a multiple linear regression model tries to explain this y response variable through p plus n random vectors, wherein epsilon is the vector of noise and x corresponds to the values of a random variable which are observable. In case of a factor analysis model, the right hand side, none of them are observable. These are vector of specific factors or simply the noise, and epsilon this f vector is a vector of random variables which are vector of unobservable random variables. They cannot be observed, right? And L is the matrix of constants, right? So, there is a huge difference as such, although the two models look similar. Now, let us go into the mathematics of this factor analysis. In order to do that, we require the following assumptions. We will put the following assumptions on the factor model. So, the first assumption, say A1, is the following. Now, this f vector, which is, as we had taken, this is an m by 1 vector. So, this m by 1 vector is such that expectation of this f vector is assumed to be a null vector. We also assume that the covariance matrix of this f vector, which thus, if expectation of f vector is a null vector, this is equal to expectation of f transpose, that's equal to an identity matrix of order m. Thus, we have these unobservable random vectors to satisfy this condition, that is, they are not only independent, they are uncorrelated random variables, they have got identical variances. So, they have got variances to be 1 for all of them. In addition to that, we require the following thing, that covariance between epsilon is our p by 1 vector. So, this p by 1 vector and this f vector, which is m by 1. So, this is going to be a covariance matrix which is going to be of the order of p cross m. So, this is covariance between epsilon 1 and f1. Like that, we will have the last element as covariance between epsilon 1 and fm. The other elements can be filled up. This is epsilon p f1. So, these are scalar quantities, scalar covariances what we have in here, and this is covariance between epsilon p and fm. So, this is the variance covariance matrix of this epsilon with f. Now, with the assumption that expectation of f is equal to 0, this covariance is nothing but expectation of epsilon vector that multiplied by this f vector transpose, right. So, we assume that this is a null matrix. So, that is the type of assumption that we usually put in for this unobservable random vector or the common factors f. The second assumption is assumption concerning epsilon. So, this epsilon is a p by 1 vector. This is such that we also take this epsilon's expectation vector to be a null vector, and the covariance matrix of this epsilon vector to be equal to a diagonal matrix having the elements say psi 1, psi 2 as psi p. These are all 0 elements. So, we denote that matrix as, without loss of any generality, we denote that equal to psi, right. So, we assume that epsilon has got this diagonal structure of its covariance matrix. So, these two are the two basic assumptions. There is a name that is attached to this particular psi I elements. These psi i's are called specific variances. The notation is nothing new actually, because these epsilon 1, epsilon 2, epsilon p, these are specific factors, and this is the variance covariance matrix attached with this epsilon vector, and hence psi i's are what are called the specific variances, right. Now, with these assumptions we will move further, and we will see this sigma matrix. If one recalls, this is what is the covariance matrix of this x random vector. By the definition of covariance matrix, this is nothing but x minus mu into x minus mu transpose, right. Now, in the factor analysis model, what we have taken is the following, that we have said that this x minus mu is written as LF plus this epsilon vector. So, this is what is the factor analysis model. Now, using that, we can write this x minus mu as LF plus epsilon into this LF plus epsilon transpose. So, this is equal to expectation of LF plus epsilon times transpose of this, which is F transpose L transpose, this plus epsilon transpose. Now, we will take the product and then take the expectation inside. So, taking the product, this is equal to LF F transpose L transpose. The second term is L F epsilon transpose, this plus this term into this, which is epsilon times F transpose L transpose, and the last term is epsilon epsilon transpose. Now, we take the expectation inside. Now, remember that this L and L transpose, both of these matrices are matrices of constants, and hence this expectation can be taken inside. This is a stochastic part here. So, we take the expectation straight inside. So, what we have is expectation F transpose times L transpose. Similar argument applied to the second, third and fourth term leads us to the following observation, that this is expectation of F epsilon transpose plus expectation of epsilon F transpose times L transpose, and the last term is expectation of epsilon epsilon transpose. So, what is this first term equal to? This is expectation of F transpose. Expectation of F is equal to 0, and hence this is nothing but just the covariance matrix of the F random vector. And what is that? That by the first assumption A1, we have covariance between covariance of the F vector is expectation of F transpose, and that we have taken as an identity matrix. So, that this is equal to L transpose. What happens to the second term? This is expectation of F epsilon transpose. Then thus this is just the covariance matrix of F with epsilon. That is what is the definition. So, we will have this is the covariance between epsilon and F is written in this form, which is also equal to the transpose of that. So, we will have this as a, we had this by the assumption as a null matrix, and hence this is the covariance between F and epsilon, which also is a null matrix. So, this vanishes, this is equal to a null matrix, and so is this. This is also equal to a null matrix, and what we have is expectation of epsilon, epsilon transpose, expectation of epsilon being equal to 0. This is just the covariance matrix, so this is further equal to expectation of epsilon times epsilon transpose. So this is equal to psi. So we have in the factor analysis model, this is the important structure what we have for an m factor model to hold. Remember, our original x was a p dimensional random vector, and f, the vector of unobservable random quantities, was taken as a p dimensional vector. Typically what we would like to have p is of cardinality to be much lower than that of m, and then actually the actual purpose of the factor analysis will be served. So we have this as the important relationship when we have an p factor model to hold for an m, I'm sorry, this is what the dimension is p. So this is the structure what we would require in order to have an m factor model to hold when we have an original random vector to be a p dimensional. So this one, as we can recall, is a p by p matrix. This is a p by m matrix of factor loadings. This is the transpose of that, so that's m by p, and this is a p by p diagonal matrix. Now a few things can be noted from such a relationship, and from this particular relationship we will first look at those before we proceed further. The first thing is what we note from this relationship here, that x minus mu is LF plus epsilon. We can look at the ith component here, so we will have xi minus mu I to be written in terms of the ith row here, Li1 F1 plus Li2 F2 and so on. The last one will be Lim Fm, the mth common factor, this plus epsilon I. So here epsilon I is the ith specific factor specific to the ith variable here. Now once we have this particular relationship here, we can see that what is covariance of xi and xk. Now covariance between xi and xk, of course, is the ikth element of this sigma matrix. Now from this relationship here, what we can see is that if xi minus mu I is equal to this, we will have corresponding to the kth variable xk minus mu k, that would be equal to Lk1 times F1, this plus the kth row, so this is Lkm times Fm plus epsilon k. Now when we are looking at the covariance between these two quantities, then since we have Fi's, what is the structure, the covariance structure of F1, F2, Fm, the covariance structure of F1, F2, Fm is that what we have assumed in A1 assumption. Where is that? This is covariance covariance matrix of this F is diagonal in nature, with covariance the variances of any of the common factors to be just equal to 1. So using that observation, what we can say is that this is just going to be the product between these two quantities, and then taking the expectation, and only this multiplied by the corresponding F1 term here is going to have only non-zero contribution. All other contributions are going to be exactly equal to 0. So what is this going to look like? This is going to look like that it is Li1, Lk1 and so on. The mth term in this sum is going to be Lim times Lkm. This plus what happens here is epsilon I multiplied by epsilon k, and then expectation of that we have assumed the following structure of epsilon, that epsilon has got this diagonal covariance matrix structure, and hence that also is going to be equal to 0. So we will have covariance between xi and xk just given by these k terms, which in terms of summation one can write this as Lij times Lkj, where j is from 1 to up to m. So the covariance between xi and xk, which is sigma ik element from the sigma matrix, is in terms of the factor loadings equal to this term what we have obtained, right. Now another important observation or note that we can make is what is the covariance between this x vector and the f vector. This x vector is a vector of observable random quantities, observable random variables, and f is the what we have defined as a vector of common factors which are unobservable. Now, by definition this is going to be expectation of x minus mu that multiplied by f minus its expectation transpose. Expectation of f is equal to 0. So, we will have this equal to this term. So, using the factor model, what we can write is x minus mu equal to LF plus epsilon, this multiplied by our f transpose. So, this is going to lead us to expectation of L f transpose, this plus epsilon times f transpose. Now, as before, this will only be in terms of expectation of f vector multiplied by its transpose plus expectation of epsilon vector multiplied by f transpose. This is the covariance between epsilon and f, which is equal to 0. So, this one is equal to a null matrix, and what we have in here is by the assumption that f has got the covariance structure as identity structure, and hence this is just equal to L. So, the covariance between this x vector and the f vector of common factors, that is just equal to L, right. Now, the third point that we can make note of is that what is variance of xi. Before we write the expression for variance of xi, we may recall that what this xi minus mu I term was equal to, that was equal to our Li1 plus f1, I am sorry, Li1 into f1, this plus Lim times this mth factor fm, this plus epsilon I. So, when we are looking at variance of xi, it is basically variance of this particular term, which is what we have as variance of xi, and then on the right hand side, if we look at variance term by term, now each of these fi's are uncorrelated with any other fj for I not equal to j, and fi and epsilon I, that covariance also is equal to 0 because we have taken that way in the assumptions. So, what we are going to get is that this is Li1 square, because variance of f1 is equal to 1. So, it is just the square here, then Li2 square and so on. The mth term is Lim square, this plus variance of epsilon I is the specific variance which is psi I. So, what we have is that this sigma II, which is the ith diagonal element of the sigma matrix, the variance covariance matrix, is equal to, this is summation Lij j equal to 1 to up to m Lij square, this plus psi I. Now, it is written in the following way because there is a special name attached to this the first quantity on the right hand side. This is, let us write that as hi square, this plus psi I. Now, it is customary to call this hi square as the ith communality. So, this hi square is what we have as a summation Lij square, summation from j equal to 1 to m. This is termed as the ith communality. Now, what does this ith communality tells us? If we look at this expression here, sigma ii, what is sigma ii? Sigma ii is variance of xi, and this ith communality, which is hi square, is this particular sum. So, this is the term which is trying to explain the variability in the xi variable, which is the variance of xi sigma ii. So, this is the portion of the variability of xi that is explained by the m common factors in total, because this is the contribution in sigma ii, or this is Li1 square is the contribution in hi square that is coming from the first common factor. Li2 square is the contribution in the ith communality that is coming from the second factor here, and similarly this Lim square is the contribution of the mth common factor fm in the communality Hi square. So this measures actually the contribution. This is basically the portion of the variance of the ith variable, of the variance of the ith variable, which is xi, ith variable xi, contributed by the m common factors f1, f2, f1, f2 and fm. So these are the m common factors, and Hi square measures the portion of the variance of the ith variable that is contributed or can be explained by the m common factors, which are f1, f2, fm. And the portion of the variance that the common factors cannot explain goes as a specific variance of the ith specific factor epsilon I, which actually cannot be captured through the introduced unobservable common factors, right. So this is what is a workable equation, actually an important equation, that sigma I equal to Hi square plus this psi I factor. Now we put as a remark the following thing, how we are going to verify this m factor model. Now we say, under the present situation, we say that an m factor model holds for x if x can be written as x minus, that is the factor analysis model, LF plus epsilon, with of course L, F and epsilon as formulated earlier. Furthermore, an m factor model holds if and only if model for x holds if and only if sigma can be expressed as sigma equal to L dash plus psi, right. So this is how one checks that a given random vector x with a covariance structure equal to sigma, whether that conforms to an m factor model where m typically is less than the order of the original random vector, that is p, that can be checked using this particular equation. So this is what it boils down, that a particular random vector x with a covariance structure sigma, we will say that m factor model will hold if and only if sigma, the variance covariance matrix, can be expressed as sigma equal to LL dash plus psi, wherein, as we said, that this L, F and epsilon are as formulated. That would imply that this epsilon is going to be a matrix which is going to be diagonal with diagonal entries. What is the characteristics of that diagonal matrix with diagonal entries as psi 1, psi 2, psi p? It is going to have those diagonal entries as positive, because this is a variance covariance matrix attached with this psi. Furthermore, if we look at this L matrix, the factor loading matrix, we had this following relationship, that in note 2 we had seen that this covariance matrix between x and f vector, that's equal to L matrix. So this is that our p by m matrix. So this will also indicate that what is the covariance between xi and fj. If we look at the ith element here and the jth element here, this is nothing but Lij, the ijth element of this L matrix. Now this divided by the variance of the standard deviation of xi is going to lead us to the correlation between xi and fj, because the variance of fj terms, f1, f2, fm, they are all equal to 1, and hence this divided by this Lij divided by the standard deviation of xi, that is root over sigma ii, that is going to represent the correlation between xi and xj. So, those are the things that would be useful when we are going for checking whether an m factor model is going to hold for a particular random vector x or not. Let us look at an example of such a situation where we are going to verify whether a particular dimensional factor model holds for a random vector x. Now, this example deals with three variables giving marks of students in number 1 mathematics, number 2 is physics, and number 3 is chemistry. So, we have this x, which is a 3 by 1 vector corresponding to a particular student, which the first dimension gives us the marks of maths, second dimension gives us the marks of physics, and the third dimension gives us the marks of chemistry, say. Now, suppose that this has got a covariance matrix, which is the variance covariance matrix of this x, say is given by this. This actually is corresponding to a standardized variable, and hence the variances are equal to 1 of each of these variables. This actually corresponds to the correlation matrix. This is 1, 0.83, 0.78, 1, 0.67, 1. We just need to write the upper triangular matrix because this is a symmetric matrix. So, this corresponds, as I said, to these three variables, standardized, and hence the covariance matrix is what actually we are looking at here, is the correlation matrix of the three random variables x1, x2, x3. Now, we will look at this as the starting covariance matrix, and we will try to answer the following question, that does a one factor model hold for x? So, that is the question. We are having three variables. We are trying to verify whether these three variables are such that, that is the sigma matrix of this three dimensional variable is such that we actually can write these three variables in terms of only one common factor. So, we start with this sigma matrix, and we are trying to verify whether a one factor model hold for x. That is, we are trying to write this x minus mu as LF plus epsilon. Now, we are saying that whether one factor model holds. Remember that when we had written x in terms of an m factor model, this was the random vector, unobservable random vector of dimension m cross 1. So, this is just going to be a scalar 1 by 1. So, there is a one factor. So, we are trying to say that now this is 3 by 1. Now, this thus L is the factor loading matrix, which is 3 by 1, and epsilon is the vector of specific factors, that is 3 by 1. Now, as we had remarked here, that we are going to say that an m factor model for x holds if and only if sigma can be expressed as sigma equal to L L dash plus psi with appropriate values of L matrix and the matrix psi. So, we are going to verify this relationship, that sigma, whether sigma is conformable to such a representation where this is L L dash plus this psi, which is matrix, I am sorry. So, this is this matrix, right, where this L is 3 by 1, this is 1 by 3, and this is a 3 by 3 diagonal matrix, right. So, this L here, what we can write is this is L11, L21, L31. So, this relationship here, that sigma equal to LL dash plus psi, this would imply that this sigma matrix, which is what we have, no need to write it again. So, sigma matrix is what we have in here, 3 by 3 matrix. Whether that sigma matrix, now on the right hand side, what we are going to do is to multiply LL dash and then add the psi 1, psi 2, psi 3, which is this psi, is a diagonal matrix with entries as psi 1, psi 2 and psi 3, and thus we are going to write this is L11 squared. So we are looking at L transpose, so this is going to give us L11 squared plus the element that is coming from the psi matrix, so this is psi 1. The second entry is going to be L11 times L21. The third entry is L11 times L31, L11 times L31. The second diagonal entry is L21 square plus this epsilon psi 2. This entry is L21 times L31, and the third diagonal entry is L31 square plus psi 3. Now this is a symmetric matrix, so the entry here is just this one, entry here is this one, and this entry is nothing but this entry. So this is the symmetric matrix. Now the question is whether we can write sigma with appropriate choices of L11, L21, L31 and psi 1, psi 2, psi 3. Whether the solution of this particular system of equations gives us valid values. Now we are going to equate the respective quantities, so L11 square plus psi 1 is going to be equated with this entry 1 here. L11 times L21 is going to be equated with this 0.83 and so on. So the solution is going to look like the following. So from the expressions what we get using the given values, what we get are the following things, that this L21 divided by L31, this is going to be from the sigma matrix, this is 0.83 divided by 0.78. Now this is going to give us, or also using this fact that L21 times L31, this is equal to 0.67. What we are doing is basically using all these values. So what we had first used was L11, L21, that's equal to 0.83, and that divided by L11, L31, which is 0.78. So using these two values, which is 0.78 and 0.83 and 0.78, what we had obtained was this this ratio, wherein this L11 term cancels out and we have this, and this L21, L31 is coming from this expression L21 times L31, that's equal to your 0.67. This would imply, using these two equations, that 0.67, this is equal to, actually this particular entry, there is no L32 element here, this is L21 multiplied by L31, so this is L31 entry, so that this term is now equal to L31 square times 0.83 divided by 0.78. So this will lead us to the numerical value as L31 square. Straight away write this L31 value, which is coming out one of these two values, which is plus or minus 0.793. So using the two equations we get this solution. Now let us take this L31 to be the value with the positive sign. After this example we are going to actually answer the following question, that whether the loading matrix is unique or not, as we will see that the loading matrix as such, when a particular M factor model holds for P, is not going to be unique. So what we are going to take is one of the two values. So L31 is, suppose we take the positive value here as 0.793. Now from here this will imply that psi 3, now look at this expression here, this term L31 square plus psi 3, that's equal to 1. So psi 3 is equal to 1 minus L31 square. So this is 1 minus L31 square, and this, using this L31 value, what we get is this equal to 0.370. So the square of this quantity subtracted from 1 gives us this. Now what is psi 3? Psi 3 was supposed to be the specific variance of the ith specific factor that was supposed to be positive, and it is in this particular case. Further, we can solve for the other values, which is L21 can be obtained from this expression, because we now know what is L31. So, we will have this divided by L31, this gives us 0.845. L21 being equal to this will further imply that psi 2 can be obtained as 1 minus L21 square, which turns out to be having the numerical value as 2.286. And we can also solve for L11, because now we have L21 value also known to us, L31 value is also known to us. So, this turns out to be 0.83 this divided by L21. L21 is 0.845. So, this value turns out to be 0.982, which in turn is going to give us this psi 1 factor, which is 1 minus L11 square, and thus this is going to be equal to 0.036, right. So, this is the entire solution. So, after solving this particular equation, that sigma is equal to LL dash plus psi, or equating these 9 values here, what we have obtained, let us summarize. So, the solution, this is L, which is 3 by 1, as we have seen, one common factor containing these as the factor loadings, which is 0.982, 0.845, this is 0.793, and this psi is that matrix of specific variances which are giving us these values. This is first entry, this is 0.286, and this is 0.370, rest are null entries. This is what thus is the solution. So, this will imply, now since we have in the original setup, this is the variance covariance matrix of standardized variables, and hence the variables when we talk about the covariance matrix is the correlation matrix. So, each of these values Lij's, L11, L21, L31, each of these now represent the correlation between L11, say, is the correlation between x1 and f1, L21 is a correlation between x2 and the only factor what is present there. This is a correlation between the third variable x3 and the common factor. And since these are all correlations, Lij's are correlations in the present setup with sigma as a correlation matrix, we should have the absolute values of Lij's to be less than 1. And what we observe in the solution is that they conform to that particular restriction. Moreover, this psi matrix that we have solved has got these diagonal entries to be all positive, and hence this is a valid one factor model. So, this implies that the 3 variables can be explained through one common factor. Now, what is that common factor? If you look at the common factor, then that common factor may be interpreted as the general ability as such. This common factor, one common factor here, this common factor can be interpreted as the general ability. Now, that of course is an unobservable factor as such, and what we have as the one factor model, the resultant one factor model would be an x minus mu, that to be equal to this L vector here, that multiplied by this common factor, that multiplied by epsilon. And hence, what if we now want to look at what is the portion of the total variance of x1, what is the variance of the x1 variable, what portion is explained by the one single common factor and what is not explained. The portion which is not explained is this psi 1 factor. Similarly, this single common factor is able to find out 1 minus this particular quantity of the variance of the second variable, 1 minus this term of the third variable. So, as we see that the first variable's variance is largely explained by the first by the only common factor, and it is actually doing this particular explanation of this order, right. So, this is L11 term, square of it, that plus this psi 1 is going to give us 1, which is the variance of the first variable as such. Here, looking at these factor loadings, one can say that x1 is closely related, most closely related to the factor, because it has got the largest factor loading, which is 0.982. The other scores here, other variables, this is what is the corresponding term to the second variable x2, this is corresponding to the third term, and hence the first variable as such is the variable. So, the mathematical ability, because we were dealing with this particular data structure, that the first variable denotes the scores in maths, second physics, and third chemistry. So, what we see here is that the loading of the first variable on the only common factor is the largest. So, it has got, it is mostly, it is a closely associated variable to the common factor, the general ability factor, the mathematical ability factor. Now, this is an example just to show whether how to proceed for a given sigma matrix and to verify whether a particular order of a factor model holds for a given sigma matrix or not. Now, just look at this particular M factor model and try to see what type of advantage we are getting if we are able to express a p-variate random vector in terms of an m-variate common factor unobservable vectors. Now, before we do that, let me give this particular remark here. We had given some numbers to the remarks. So, let me just write this as remark number 1. Then this remark number 2 is that when we take m to be equal to the number of original variables p, sigma can always be represented, can always be written as sigma equal to LL dash plus psi with psi equal to a null matrix. Because sigma is a positive semi-definite matrix, at least we can assume that it is positive definite, so that there are no redundancies. So, this sigma matrix is equal to LL dash, that will always be possible with this psi matrix to be equal to a null matrix. But what we are doing here, we are expressing p variables x1, x2, xp in terms of p common factors only. So, there is no reduction as such in this particular situation. So, this case is basically of academic interest. This case is of no interest, actually, no interest, since we are using p common factors for p variables only. Now, the actual usefulness of this factor analysis is going to come if we have this m here, the number of common factors is significantly lower than that of the original starting variables. And what is that we are going to gain? We are going to gain the following. Let me put it in remark 3. As in the previous case, we had 3 variables, 3 original variables x1, x2, x3, and we had expressed that through one common factor. Now, here what we are concerned about is reduction in the number of parameters, for an M factor model. Now, parameters in terms of the sigma matrix, because we are trying to explain the variance covariance structure. So, we start with this sigma matrix. This is a p by p matrix, this is a symmetric matrix. So, the number of quantities So, the number of quantities that is there in the distinct elements in sigma are p into p plus 1 by 2, which is diagonal plus the upper or the lower entries. Now, suppose I have expressed this x in terms of an m factor model with x minus mu written as LF plus epsilon. This is, say, I take this one as before p by 1, and this is, say, m by 1 common factors. So, here what we are looking at is sigma to be expressed as LL dash plus psi. Now, what's the number of parameters that we have in here? In case of this m factor model, this L is what? This L is a matrix of p by m constants. So, this is p by m number of entries which are there in L, and this psi, remember, is a diagonal matrix of this p order. So, there are p entries which are there in this. So, collectively in the m factor model, so this is for the m factor model, what we are going to have is this Pm plus P. So, the reduction in number of parameters, is, this is the original setup. What we have is p into p plus 1, this by 2, this minus, this is Pm plus P is the number of parameters which are there in the m factor model. So, simplifying this, what we get is p by 2 into p plus 1 minus 2m minus 2. Take a particular example. This is the reduction in the number of parameters when we are able to express, say, an p variate random vector by an m dimensional model. So, the example here, if I take p equal to 12, m equal to 2, so we have 12 original variables to start with, and suppose we have been able to express those 12 variables in terms of 2 common factors, then this term here, which gives us the number of reduction in the number of parameters, if you calculate, this will turn out to be equal to 42, which is huge actually. So, by using a 2-factor model to a 12-dimensional original variables, we are able to reduce the number of parameters which is explaining the variance covariance structure sigma through the m factor model. For with m equal to 2, we are able to reduce the number of parameters to 42. So, we will continue from this in the next lecture.